Welcome to Multidisciplinary Design Optimization, lecture number 3 on design space exploration. I would like to briefly review what we talked about last time. So if you remember last time, we encountered unphysical behavior in one of our models for the 2-bar truss, and we took that as a hint that there may be an error in our simulation model. And in fact, there was one. There was a sign error, and we eliminated it. So I advise you to take any suspicious behavior seriously, because you can save a lot of time when you eliminate errors in the beginning before you run your optimization and do not have to trace back unplausible results all the way to the beginning of your analysis. There is an important distinction between unconstrained and constrained problems. Constraints come from requirements on your design or restrictions on your design space, and constrained problems are typically the ones that are more difficult to solve, but also the more interesting ones, because those are the ones that you encounter in industrial practice. We started with the fundamentals of optimization, looking at simple one-dimensional problems with one design variable and one objective function, and then made the step to a two-dimensional input space and an objective function and a constraint function. So a two-dimensional output space, so to speak. There are important characteristics of optimization problems that will help you pick the right algorithm, or they will help you to draw the right conclusions from data that you encounter. For example, convexity, which says that between this line here, any function values will stay below. And that tells you that whenever you encounter a local optimum, it also will be a global optimum, and you can stop your analysis. Whereas non-convex problems, for example, when the objective function is non-convex problems can also be non-convex because their constraint functions are non-convex. Then you may run into local optima, and you cannot conclude that this is the global optimum because this may be somewhere else. And you would have to keep on looking if you are determined to find the global optimum. Another important property is linearity of optimization problems. And optimization problems are linear when the objective function and the constraint functions are linear with respect to the design variables. And when you have a linear or a monotonous problem, then your optima will always be at the boundary. Monotonous functions do not have to be linear, but they will always decrease or increase in value upon increasing design variables in one direction. For linear or monotonous problems to be well-posed, you need boundaries. Well-posedness means that there is a unique solution to your problem, and if a non-monotonous or non-linear objective function is to be minimized and you do not have a bound, then mathematically speaking, there is no solution to the problem, and your algorithm will just keep on running and running and increasing a design variable value and increase it further, and you will never find a solution. Let's get started with today's lecture, design space exploration. And we will be talking about how you can explore the design space and understand the structure of your optimization problem by using formula analysis, or a technique that is very often used in the analysis of high-dimensional problems, high-dimensional optimization problems, that is sampling. And we'll also be talking about quantities that you can extract from your optimization problem to learn something about it, which are called sensitivity measures. For understanding your optimization problem, it is very helpful to understand of what kind your objective function or your constraint functions are. So what you would like to know is what structure the function has, how input and output are related in general, which can be used, for example, to assess the importance of design variables, such that you can simplify your analysis, for example, by neglecting unimportant design variables. That is particularly difficult when you have nonlinear functions. That means that your change of output is not proportional to your change of input, or you have noisy functions, which means that, well, strictly speaking, the same input will lead to different outputs. But let's say from a more practical perspective, you could also call noisy functions that produce strongly varying output under very small variations of your input. Another troublemaker is if you have many input variables or many design variables that are relevant simultaneously, and then we call our problem a high-dimensional problem. And it becomes particularly difficult when they start interacting with each other. So when they both affect the value of your function simultaneously. And also when you have functions only available as black box functions and you cannot look at formula, then you're restricted to carefully checking what output is produced by what input and evaluating that. So when you do have formula available, we can make use of that, for example, to get an intuitive understanding of our problem. You can use also the formula for something that we did last lecture. You just systematically plot input-output relations. So how your objective function changes when you vary your design variables, for example. Or you can use formula to derive sensitivity measures that we will be talking about in the end of the lecture. When you do not have a formula available, then you need to use a different technique, which we call sampling. And sampling is a technique where you, according to a particular scheme, produce sampled designs and you compute values for your objective and constraint functions and try to systematically derive formula that measure their connection, that quantify their connection, for example, by computing sensitivity measures or other statistical measures, or by deriving mathematical surrogate models. So the two large chapters for today will be formula analysis and sampling techniques. So like last lecture, we will proceed in an inductive way. That means we look at a small particular problem and then slowly make it bigger to end up with a general understanding of what we're looking at. Let's get back to our two-bar truss. And so remember, we have a quantity of interest. In this case, that is the tip of the displacement. And we have a bunch of design variables. The load that is applied to the tip of the two-bar truss. Young's modulus, we have the reference length L and a cross-sectional area and an angle alpha as a design variable. This is what we call our reference design. And now we're going to perform a very basic analysis, which is plotting, of course, which is trivial. So we just look at how our objective function changes with respect to our design variable. And we realize, which can also be confirmed by the formula, that we have a linear relation between input and output if your design variable is L. The function is convex, and it is also monotonous. That's simple. Let's look at another example. If we choose as a design variable A, then our problem is nonlinear. It is still convex, and it's monotonous because you can tell that it's always going downhill by the plot, but you can also tell by the formula. Here you can see that u as a function of A is a hyperbola, provided, of course, that you keep all the other design variables fixed. So when we choose alpha as a design variable within our design space, then we encounter a behavior that is nonlinear. It is still convex, and it's not monotonous anymore because it goes downhill and then back uphill. Now let's increase complexity a little further, and let's look at an example with two design variables, the cross-sectional area and the reference length L. And we look at the plot and at the formula and find out that our problem is nonlinear, or the function is nonlinear. It is convex, and it is monotonous. When we increase complexity even further by adding one more design variable, so design variable alpha, then we're done using plots and formula analysis. Unless you have a very strong intuition for analytical formula, it'll be difficult for you to assess what the relation between your system response U and these three design variables will look like. Of course, you could start by repeating the previous analysis of plotting, for example, U with respect to A and L for, let's say, 3 different values of alpha, something you can do. But then the latest, when you add yet another variable, that'll be very complicated, and you won't get much insight from that. So the problem we have is that the means to visualize the structure of functions with more than 2 design variables, they're very limited. So the question is, how can we visualize dependencies or make them more intuitive when we have more than 2 input variables? So, and this is our technique that we'll be using. It's called sampling. And I'd like to briefly talk about what we mean by sampling. A sample is a collection of design vectors and associated output values where we use this notation. Capital A will be our design index running from A to capital N, and N is the number of designs, or also called the sample size. What we will do for the next chapter, for this chapter, is that we will only talk about one output value. So m, lowercase m, will be set equal to 1. But whatever we will discuss is, of course, applicable also to the second output value and the third output value separately. Designs are chosen according to a sampling method when you do sampling. And a synonym for a sampling method is also design of experiment. So you probably heard of this. And please do not confuse design of experiment with something that you design as a physical object. So here, what we mean by design is really a generalized idea of design. So you specify something for a particular purpose. In this case, you specify the positions of your design vectors that you use to probe your function. So sampling is used to probe the design space. You can really think of it like like each design as a little scout that goes there and sees and checks what function value will be produced. And or you can think of it as a poll, like a political poll. When you would like to forecast what party will be elected in next election, you just randomly can call people and ask them who they would vote for. And when you ask the first person, they would say party A, and then the second person, party B. Then you have an idea, and that idea will become more and more accurate the more people you call. Once you called 1,000 people, and 200 of them said they will vote for party A, and 500 said they will vote for party B, then it becomes more and more likely that this is representative of what the entire population would vote for. And the same mechanism essentially is used in the analysis that is based on sampling for our purposes here. Sampling methods can, of course, be applied to problems or to functions that are analytically available, where you have the formula, but they are really useful for black box functions because you can compute the output values YA for black box functions. And this is all you need. So you don't need gradients, you don't need analytical information about your function. And this is what makes sampling methods particularly helpful or useful for the analysis of black box functions that we typically have in our optimization problems. So let's start with the first sampling method or the first design method. It is called a full factorial design, and this is probably the most intuitive approach that one would think of. So what you do is you specify within your design space, you specify a set of levels. So in this case here, you would choose 2 levels of values that design variables can assume, and you do that for one dimension and for another dimension and all dimensions that are relevant. And what you typically do is that you would choose your levels equally spaced, and then span or define a grid with all combinations of level values for each design variable. So this here would be an illustration of a sample where you have 3 levels, and the number of sample points you would produce this way would be 3 times 3 times 3. So, and then it's easy to understand that in general, the number of sample points you would produce this way is the number of levels to the power of the dimensions of your input space. So you can see that capital N will become large pretty quickly upon increasing the number of levels, and in particular upon increasing the number of dimensions of your input space. Let's apply this to example 4 and see what comes out of it. So to remind you, sample 4 was our 2-bar truss with cross-sectional area and the reference length L as design variables. And now we use a 3-level design for our 2 design variables, equally spaced. By equally spaced, what we mean is the distance here is the same as this in a normalized sense. So normalized with respect to the design space. And what you do when you, after you created your sample design, you would compute the function value for each design point, and you would get these blue dots. Since we know the formula right now, we still do it because we have the formula explicitly available. We can also plot this this black surface, which is something, of course, you would not get by sampling. Okay, we just add this information because I would like to make the step from something we can imagine towards something that is more difficult to imagine, which will be a situation where we only have these dots available. We can look at these results here in so-called scatter plots. Scatter plots are the projection of these blue dots onto 2 dimensions, and what you see here would be the projection onto an LU plane. So essentially we're looking this direction, and well, you can imagine how these 9 points would arrange like this. Or when you look this direction, the 9 points would arrange like this. And I would like to make a connection also to what we previously saw. These here are plots where for a fixed cross-sectional area, we looked at the displacement, the change of the displacement with respect to the base length L, but only for one cross-sectional area value. And what you see here is the change of displacement with respect to the cross-sectional area, but only for one fixed reference length value. So this is a projection on the right-hand side in the scatter plot, versus this is a section on the left-hand side. When you make a section, you lose information. In particular, you lose the information of those plots that you would obtain if your reference length had a different value than the one that you assumed here. Or in turn, you lose the information that about all those functions for different values of the cross-sectional area A. In the scatter plot, this information is still included. So that is helpful, and we will be using that for more complicated examples. Let's look at the full factorial design of a 3-dimensional problem now. In particular, one where we choose the cross-sectional area, the reference length L, and the angle alpha as a design variable. And remember, that was the first example when we said formula analysis is already pretty difficult. And now let's apply sampling to this. We use a 3-level full factorial design, and we come up with 27 sample points or sample designs. And since we can't make a plot now anymore, since we have 3 design variables, we will have to rely on the scatter plots now to understand what's going on. And now what you can see here is that rather than those 3 values we had here before, in the plot before we had 3 points for one particular value of L. Now we have 9 points. And the reason for that is that these points here, they are not only for varying A now, they're also for varying alpha. So remember, we added one design variable and we varied this in our sample design as well as A and L, of course, but L here in this diagram is fixed at 500 millimeters and A and alpha do change. And now you get an idea of what L does to the function output while the other design variables, A and alpha, are still varying. And the same is true for the other scatter plots. So you can tell that upon increasing the reference length L, the largest range of displacements will be possible. If you make L small, so you restrict it to 500 millimeters, you can tell that apparently there's no displacement above about 12 millimeters possible, regardless of what you do to your cross-sectional area and your angle alpha. Because if it were otherwise, you would see a point here, but you don't. So this already tells you that L has this kind of influence. Upon making L small enough, you can reduce the displacement to something below 12 millimeters. The same is true for the cross-sectional area A. If you make A large enough, you can reduce your displacement to a value below something like 15 millimeters. Another interesting result you can see here, when alpha assumes its middle value, then apparently it doesn't matter what the other design variables do anymore. So scatter plots provide a possibility to represent functions of higher dimensions that you could not visualize otherwise anymore. Let us now study how variables with little influence can be detected. And we will do that by creating a problem, a design problem, with one irrelevant variable. So this is the extreme case that is meant to represent what will happen with irrelevant or with variables of little relevance. Let's take example number 3 and add the age of technician as a design variable that of course has no influence. So formally we add the age of the technician to the argument of our objective function. And we keep the formula as it is. So the age will not enter the formula. We create a 3-level full factorial design in the 2-dimensional input space, and we can look at the system response and the quantity of interest, our displacement u, as a function of a and alpha. And of course, little surprising, the output will not change if you change a. When you look at the scatter plots, you find out that that alpha seems to determine u uniquely. So this is what we observed in this 3D plot too, but in the scatter plot, which we can also create for higher dimensional problems, we can now relate this information, that apparently there is little variability of the output function for one fixed value of alpha. We can extrapolate this to higher dimensional problems. When you look at the scatter plot on the right-hand side, you can see that the age of the technician doesn't do much to the output. Regardless of the age, it'll always be these three system responses, which are, of course, determined by u. And since u does not vary upon changing the age, that's a strong indication that something that looks like this is a hint at little or no relevance. Something that looks like this is a hint at strong relevance. Since relevance is difficult to assess in higher dimensions, scatter plots are a useful means to assess relevance for those cases. Now let's try a more complicated example. Let's look at example 3 that we just had, and now let's add 3 irrelevant variables. So we add as a design variable the age of the technician, the color of the truss elements that we used, and let's say the height above sea level of the 2-bar truss. We formally add them as arguments to our objective function, but we do not change the analytical function for our quantity of interest. And of course, we cannot produce a 3D plot now because we have too many design variables. But what we can still do is we can look at the scatter plots for a full factorial design now of 81 design points. And now you encounter the same what we saw before. The only relevant variable uniquely determines the value for the quantity of interest. But now we have 27 design points on top of each other. And before we had only 9. And the plots for the irrelevant variables, they all look the same. Not surprisingly. So good news is that using scatter plots, you get a very good idea whether or not a design variable is relevant or not. The bad news is that you pile up all these points on top of each other, and although you invested into a lot of function evaluations, you only have little information here. And that's one of the disadvantages of full factorial design. We're going to generalize that later. But now let's take that as a hint that we want something that is somehow more efficient, that adds more information to this kind of evaluation. And this is a new sampling technique that we're going to look at now. Random sampling is similarly to full factorial design, used to probe the design space, and it's very different. Full factorial design is the extreme case of a structured design. So you really systematically try to cover the design space in a complete sense, in a systematic sense. Random sampling works differently in that it creates its sample points randomly, obviously. And so formally we have a random variable xi that can assume values between 0 and 1. And the random variable will be uniformly distributed. So it is associated with this probability distribution. The probability distribution is 0 outside the interval from 0 to 1, and it is 1 on that interval. And you compute your sample points using this formula. So for each design variable, you have a lower limit and an upper limit of your design space. And xi tells you where on that design space interval for that design variable your design will be located. So the number of sample points you choose can be arbitrary. So you can choose 3, you can choose 100 or 1000. And well, this is particularly useful when your function evaluation is very expensive and you, for example, have a limited budget of computation time. Then you can just start computing your sample, and once you're out of your budget, you stop. Whereas if you run a structured design of experiment, you would typically have to complete a particular scheme. And that may become a problem when you have simulations that that crash, that that abort, not producing an output value, leaving a hole in your sample design. With Monte Carlo, you don't have this problem. You just skip that one design and use the next. Whereas in a full factorial design, you would have a hole. And that may change the properties of the conclusions that you're trying to make from the analysis based upon that design. So another important keyword that should be mentioned here in this context is Monte Carlo. Well, there is a family of methods that relies on random sampling, and those methods are called Monte Carlo methods. And the name was probably chosen because there are lots of casinos in Monte Carlo, so randomly choosing design variables is somehow associated with this idea of chance, and that supposedly led to the name of these methods. So there is an element of chance involved in here, but I will show you that this kind of sampling is actually extremely powerful, and for arbitrary problems, in particular nonlinear and noisy problems, preferable to structured design methods. Well, let's now look at our examples using random sampling. And let's start by example 4 with 2 design variables. So now our sample looks different. You can see here how our design points are randomly distributed and produce, of course, different points here on our response surface. And if we when we project them onto our UL and UA plane, we can tell that, yeah, it looks less structured. But you can still see how U increases upon increasing L, or how U decreases upon increasing A. Let's compare it to what we saw before. And as an important difference, you can tell that the holes that you had here in your scatter plot, they're gone. Now you have values in between. And this is one of the major advantages of random sampling. And you can actually see that on the problems to come even better. So now let's look at example number 7, where we had 1 relevant and 3 irrelevant design variables. We cannot look at the full response function or the surface that the 3D surface that we use for 2-dimensional input spaces anymore, because there are too many design variables involved. But we can look at the scatter plots. And now what you can tell is how even in that high dimensional setting, you can very well extract the dependency of U on alpha. So this is the result for random sampling, and this would be the result for a full factorial design with comparable number of sample designs. So you can tell that these holes here, they are closed. And it's a little more difficult to tell whether A is irrelevant or not due to the random distribution of dots. I mean, in this diagram, you could think, well, perhaps there is a slightly decreasing tendency. So the displacement will become smaller when the age of the technician increases. And that, of course, would be wrong. Yeah? But, well, when you increase the number of samples, or the number of sample points, then this plot would become more and more dense. And it'd be easier to detect that this variable is in fact irrelevant. Now let's look at an even larger input space, or higher dimensional input space, with 3 relevant design variables and 3 irrelevant design variables. So we have a 6-dimensional input space. And if you did not know which of these variables were relevant and which not, because it's a black box function, it'd be difficult to assess that. Now let's look at the scatter plots of a sample that was created using random sampling and compare it to the scatter plots that were created using full factorial design. And again, you see these large gaps in the full factorial design, whereas here on the right-hand side, you have all these design points in between. So you have, in some sense, more visual information that will help you to assess the dependency on this explanatory variable or design variable. You could not clearly conclude from this scatter plot that A is irrelevant because due to the random nature of the sampling, it is not perfectly evenly distributed. So you could conclude this here, but then of course in reality design variables will mostly not be perfectly irrelevant, so you will also have little variations here, and you would be as inconclusive as with random sampling. For the relevant design variables, you can identify structures. So you could not conclude, of course, that this is a parabolic dependency, because you always look at an average over the design space. So meaning that when you look at the designs for a fixed value of alpha, you will get a random choice of all the other design variables. So in some sense, you look at the projection of this point cloud onto the alpha U plane. And you don't know whether these are all something that is parabolic, more or less, or maybe something different, because you can only look at the projection. For those explanatory design for the relevant design variables, you get in both cases some idea of what the dependency looks like, but again, you have these gaps more densely filled for random sampling. Let's look at example 7 and 8 again and draw two important conclusions. Well, the first conclusion is that the more relevant design variables you have, the more difficult it will be to detect them by sampling. And I'm going to show you this here using the scatter plots for random sampling, but actually this conclusion is also true for full factorial sampling. And you can tell when you have three design variables that are relevant, your scatter plots for relevant design variables and your output quantity, they will look somewhat blurry or fuzzy. If you only have one design variable, you can identify a very crystal clear dependency. And the reason for that is simply that the variation of U does not only depend on L, but also on A and on alpha. So, but now imagine that you have a limited budget of sample points and you have a large number of irrelevant design variables. Well, if you add irrelevant design variables and you have a limited budget of sample points, then the number of levels would be very small. And well, in the extreme case, you only have one or two values of alpha that you can probe, because you need to take care of all the other irrelevant design variables. So you would waste all your design points on varying design variable values of irrelevant design variables, and you could not easily conclude that alpha is in fact the most relevant design variable. Or even this picture here, this would not change if you added 1,000 more irrelevant design variables. The dependency on those three relevant design variables would stay the same, or the scatter plots would actually stay the same. So in the extreme case, you could even identify those three relevant design variables with a sample size of 400 design points in the presence of, say, 1,000 irrelevant design variables that wouldn't matter. See, and this is one advantage of random sampling. So you can identify few relevant design variables at a lower numerical cost. So far we have talked about only synthetic problems to keep things simple. Now let's look at a real-world industrial problem from BMW. It is a problem from an early design phase, and it is about chassis design. I will briefly comment on the components that you have an idea of what this is about. So in the rear and in the front axle, there are a couple of mechanical components, and we need to optimize their stiffness or geometry quantities like the operational point of the bump stop. So the components involved are the anti-roll bar, which is a torsional spring preventing the vehicle from rolling too much. Then we have a bump stop element that softens the impact when you hit a bump on the road and the vehicle is abruptly accelerated upwards. And then there's also a so-called rebound stop, which is a spring within your shocks that will prevent impact from the wheel moving downwards too abruptly. And then also another design variable would be the wheelbase, the position of the center of gravity, and the total mass of the system. So this is just to give you an impression. We're not going to discuss the physical behavior in detail. But what you should know is that we have 12 design variables in total, which is quite a representative number of design variables that you would have to typically consider simultaneously. You could even say that it is a small number of design variables. And now let's see what we need to consider as a load case. As a load case, we are, in general, this chassis will be designed. We're not going to consider all these load cases, but just to give you an impression, according to what load cases they are designed, you would look at a driving maneuver, which is called quasi-steady state cornering, where you have to maintain a certain maximum lateral acceleration of your vehicle. Or another important quantity of interest would be the distribution of the so-called roll moment distribution. In German, it would be Wankmomentenverteilung. But this is, I guess, only for experts of vehicle dynamics. And but what we will consider here is the so-called sign withdrawal maneuver, where you perform a double lane change, and your design goal is that the vehicle does not lose stability, driving stability, and we will measure this by a quantity of interest which is called the maximum of the slip angle. Okay, so this would be the most important quantity of interest. Here you can see, you get an idea of how this quantity of interest changes with respect to time. Let me correct this. The quantity of interest itself does not change with time. The quantity of interest is the maximum of the slip angle, but the slip angle changes with time according to this curve, and the maximum should stay below a particular threshold value in order to maintain stability. Okay, and then there are other quantities of interest we are not going to consider. That would be, for example, the normal force that is exerted by the wheel on the street, which measures how close you are for the vehicle to tip over. So to summarize, this is our quantity of interest, maximum slip angle measured in this maneuver, sign withdrawal, and we have 12 design variables to change it, to affect it. The corresponding dependency graph would look like this, and we will focus now on this analysis where only one quantity of interest will be analyzed, and in particular the effect of those 12 design variables on that quantity of interest. This is the result of a random sample with 12 design variables, and this looks pretty representative of what you often get. So there is no clear distinction between the relevant and irrelevant design variables. Actually, most design variables look pretty irrelevant. The most relevant seems to be this one here. That would be the anti-roll bar stiffness in the front. And this is actually also what you can explain physically, and what you can confirm if you run more detailed analyses. If you compared this to a full factorial design, you can quickly realize that this wouldn't produce very meaningful results here. So if you did a simple two-level full factorial design with 12 design variables, you would end up with 4,096 simulation runs. And so you have 4 times the effort and have much less information. So you don't see anything what's happening in between. And therefore, in this case, with 12 design variables, the random sampling would be preferable. So let me comment briefly on other sampling methods and then summarize. In addition to full factorial, there is also a fractional factorial sampling method. And fractional factorial methods significantly reduce the number of required sample points. That's nice, but then they work particularly well only for particular functions. You can also use design methods that are, well, somewhere between a non-structured, purely random design and a structured design. For example, there's the so-called Latin hypercube sampling method, where you still pick randomly designs, but only within within particular slots. So for example, here you make sure that each line and row will only get 1 sample point. The exact location within that little square will be chosen randomly, and what row and what column will also be chosen randomly. And this is a way to somewhat controlling that you don't have large holes in your sample. Well, however, in high-dimensional problems, in my opinion, it doesn't make a big difference really to random sampling. And also for optimized Latin hypercube sampling, where you explicitly try to minimize the distances between sample points to get a good coverage of your design space, even that does not significantly improve the results of high-dimensional design problems, in my opinion. But there are other opinions out there, and I guess then it depends a lot on the particular problem that you're trying to solve or that you're considering what methods works best. So I would summarize this chapter here by saying that you can sample in a smarter way, definitely, and that can produce better results. But then you're typically restricted to particular functions, or when you're using sampling schemes that rely on a complete set of samples, you may run into problems when simulations abort. So for our purposes, random sampling is the method to choose. It is simple, it is reasonably cheap, and it is applicable to pretty much all functions, not pretty much, sorry, to really all functions. So there is no requirement on linearity or noise or whatsoever. It's just a very robust, simple technique to use, and in my opinion, the one that is to be preferred if you do not want to make particular assumptions about the function. I find high-dimensional design spaces quite non-intuitive, and I guess most people find that too. And in order to train intuition for higher dimensions, I would like to tell you about 2 curious effects in high dimensions. For the first effect, please think of the distance of 2 design points, like shown here. So there's a design point called XA and a design point called XB. And the distance in high dimensions would be given by this formula. It's the square root of the sum of squared component differences. Now that's fairly straightforward. Now let's think of the distribution of all distances of all pairs of design points. So let's not only consider this one particular pair, but let's think of all possible pairs and count how frequent distances are. That will lead us to this plot. In one dimension, you can tell here by these yellow bars, small distances are more frequent than large distances. To imagine this, you can look at this one-dimensional design space shown here with a random collection of design points. And here you get an idea that small distances are more frequent than, for example, large distances. So the largest distance here, for example, would be very rare because you would only encounter this when you look at the pair of points in the beginning and the end of the interval. Let's increase dimensions. Let's go to 2 dimensions and now try to get an understanding or a feeling for how distances are distributed here. You can tell by just looking at this plot that the small distances will become less frequent. The points are moving further apart. And this is reflected by this blue plot with a peak at about 0.3, where this graph actually is normalized by the distance value over the square root of dimensions. When you increase dimensions even further, so if you go, for example, to 10 dimensions, distances will become more concentrated, here at about 0.4. And when you increase dimensions even further, then this peak will become sharper and sharper. And in the limit for the number of dimensions going to infinity, you will essentially have only one distance between 2 randomly chosen pairs. Or in other words, small distances between pairs will be extremely unlikely, whereas most points will have the distance right at the peak. We will provide a MATLAB code on Moodle that you can execute in order to produce these graphs here and study it yourself. So the consequence of this is that all sample points in high-dimensional spaces have similar distances from each other. And another consequence is it'll be very difficult to classify regions of good and bad designs. So to tell apart what design is good and what is bad, because they essentially all have the same distance from each other. So this is the first curious effect that I would like you to think about. For the next effect, let's think of what I call regions of interest within your design space. A region of interest would be a region of designs that satisfy requirements or constraints. And this region could be represented by a fixed interval for each design variable. And now let's assume that that region of interest is such that for every design variable, that interval is the same. So what happens when we increase dimensions? When we add another design variable and another design variable and yet another design variable. And all these design variables are relevant in the sense that whenever you are within that interval, your design is interesting because it satisfies certain requirements, and when it is outside, it is not. Yeah? And you don't like the design because it violates some requirement. So when you increase dimensions, then the volume of the region of interest divided by the volume of your design space would be r to the power of d, where r is the ratio of the interval size for the region of interest and the design space interval size. And now let's say for each design variable, 50% of the design space would even qualify for region of interest. Then the volume ratio of region of interest and design space would be this. And when you look at 100 dimensions, for example, the volume ratio would be 10 to the power of minus 30. So in other words, although for each design variable, the interval ratio is pretty big, it'll be extremely difficult to find that little pocket of region of interest in your design space. So in other words, if you're looking for that region of interest and you have no help to guide you towards that region, you would, if you did that search, for example, by brute force sampling, you would need on the order of 10 to the power of 30 sample points to have a realistic chance of finding it. Thank God in optimization, in numerical optimization, you do have help, which is given to you, provided by gradient information. But sometimes you do not have it. And when you do not have it, then you need to rely on particular search algorithms that need to overcome this difficulty that regions of interest are extremely well hidden in a high-dimensional design space. Another consequence of this effect is that whenever you establish information about the entire design space, like relevance of design variables quantified by sensitivity measures, for example, you lose all of that when you zoom in a little bit. So any statement about the entire design space would be essentially lost when you focus on a region of interest with only half the interval size of the original design space interval size. So that's another curious effect that I would like to show to you to make high-dimensional design space a little more intuitive. I hope that helps a little bit. Okay, let's talk about sensitivity measures as the last chapter for today's lecture. In our lecture, sensitivity refers to a measure of the variability of the output depending on how we vary the input. There are other notions of sensitivity, but this is what we mean here in this lecture, and it is meant to give an idea of how important design variables are, so that you can distinguish unimportant design variables from important design variables to reduce the size of your problem or the dimensionality of your problem, for example. So the sensitivity measures that we are going to talk about here is the correlation coefficient, the gradient or components of the gradient, and regression coefficients. So what is a correlation coefficient? Let's look at 4 examples and think whether we observe a good or a bad correlation. So in the first example here on the left-hand side, we observe a good linear correlation, and from that we can conclude that L is a relevant design variable because by adjusting L, you can adjust U. So L explains all the variability in U. This is what we also observed when we talked about the scatter plots in the previous chapters. For the relevance of L, this is sufficient, but it's actually not necessary. Saying that L may be relevant even though you do not have a good linear correlation. So when we look at the second example, we can observe that there is a moderately linear correlation and L is somewhat relevant, as opposed to the third example where you can clearly say there is a bad or no correlation. So changing L does not seem to have an effect on U. And in this case, you cannot conclude whether L is relevant or irrelevant, because there are cases when you see something like this, but L is still very relevant. So when you look at the final example where you observe sample points on a parabola, you can see that there is no linear correlation, there is only a non-linear correlation. And L is relevant because it will tell you exactly what U will be. The formal definition of correlation is given here. So for our sample points with a sample point index A, capital A, running from 1 to n, we define the mean of design variable I using this formula that you are familiar with. We define the standard deviation of the variable design variable I using this standard formula, and the so-called covariance, which is the sum of the differences of the design variable value from its mean multiplied by the output value from its mean. So this is the covariance between design variable I and the output y. And the definition of the Pearson correlation coefficient is the covariance divided by the standard deviation of design variable I and your output y, given by this formula. Now let's look at the correlation coefficients for the examples that we just looked at. In the case of a strong linear correlation, the correlation coefficient evaluates as 1. It could also evaluate as -1 for a for data points running like this. The correlation coefficient for example number 2 would evaluate as 0.53, which is due to the fact that the design points are not on a line like in example 1. And the correlation coefficient of this example here would evaluate as approximately 0. And the correlation coefficient of the fourth example would also evaluate as 0. So you can see that for a correlation coefficient being 0, you cannot conclude, you cannot strictly conclude how relevant a design variable is. However, if it is 1 or -1, then this is sufficient for a design variable being relevant. So the correlation coefficient quantifies to what degree the relation between two variables is relevant, and to what degree the relation between two variables can be expressed as a linear function. It is sufficient, but not necessary for the design variable being relevant. So the next sensitivity measure is a gradient that you're all familiar with. A gradient is a vector of partial derivatives with respect to different design variables. For functions that can be expressed analytically, the gradient can also be expressed analytically. However, we are in trouble when we want to find gradients for black box functions. If we have black box functions, then derivatives need to be approximated numerically, which can be expensive if we have many of those design variables. And one way to do that would be using central finite differences, meaning that for each gradient component, you compute the function value one step ahead and one step back for each design variable and divide it by twice the increment. So when people talk about sensitivities, they typically, or very often, they mean gradient components. Okay, so this is a narrower notion of sensitivities. We also call the correlation coefficient and the regression coefficient a sensitivity measure as a broader concept of sensitivities. But when we talk about the sensitivity, that people typically mean the gradients themselves. So the third type of sensitivity measure that we are covering here is a so-called regression coefficient that we derive from a mathematical surrogate model that we train using sample data. For the regression coefficient, we use one very particular surrogate model, and that is a linear regression model, which you're also familiar with. I'm going to go quickly through the math to explain how this is carried out. So we want to approximate our black box function f of x by a substitute or a surrogate model f hat of x. And we do that by assuming a linear structure for the surrogate model. And this is appropriate, of course, only when your black box function is behaved well enough that you can do that. So if you have a strongly nonlinear black box function, then this of course doesn't work. So you have the sample data available, your collection of design vectors and corresponding output values. And now let's introduce a particular notion that is helpful to go through the math. Let's call x tilde an extended design vector that also includes one component that is just one, and that is done to simplify the math, so you can express your linear approximation or a regression model as a dot product of these two vectors, x tilde times beta. And in beta, you have all the coefficients that need to be adjusted for this regression model to resemble the original black box function. So you can think of the regression function now as something that approximates f up to an error epsilon. And in order to adjust beta, we want to minimize the error. And since the math is easier, if we minimize the error, the square of the error, we do that. But this is equivalent to minimizing the error itself, or the absolute value of the error. So let's use this formula, plug it in here, substitute this expression by our definition of beta. And when you carry out the math, you come up with this, where y, capital Y and capital X are defined as matrices, simply as a matrix of all sample values for your design variables. So all the sample designs are in here. So this would be sample design number 1. This is the sample design number 1. This is sample design number 1. This is sample design number 2, and so on. And here we do have our output values. So Y, I think I just said it's a matrix. I have to correct this. Capital Y is a vector. So minimizing the error squared with respect to beta, the coefficients that we're interested in, that we're after, that we would like to adjust such that our regression model performs well, will give you this expression. And if you carry out the differentiation with respect to beta, you come up with this. So if you don't want to do this in a complicated vector notation, you can do that component by component. But it is pretty straightforward. You'll end up with a term where you first take the derivative of beta of this expression with respect to data times this, plus this expression times the derivative of this thing here with respect to beta. And then you pull out the X matrices and invert them, and you'll end up with this expression. So let's compare how our coefficients beta, which are the regression coefficients, how they are related to our correlation coefficients. And for that, we'll look at the examples. In the first example, we had a correlation coefficient of 1, and our beta turns out to be 1.8 times 10 to the power of minus 3. In the second example, we have a correlation coefficient of 0.53, and the regression coefficient turns out to be larger. In this example, we have a correlation coefficient of almost 0 and also a regression coefficient of almost 0. And in the last example, we have a correlation coefficient of almost 0 and also a regression coefficient of almost 0. The regression coefficient and correlation coefficient, they are related. And I would like to explain this using our little example here. So you can think of the regression coefficient as an average slope. So remember, we derived it from the best linear fit for these design points. And if your design points are distributed, then you somehow average them in order to fit the best linear approximation. So now think of the blue dots being aligned on one line. Therefore, the correlation coefficient would be 1. And in this case, the regression coefficient would just be the ratio of variability in U and variability in L. It would be just delta Y by delta X with the blue dots being on this line. Here, the correlation coefficient is not 1, it is less. And that will make also the regression coefficient less, because now the points are just distributed, and that will affect this averaging of our slope. So this is a qualitative explanation for this formula. This formula holds in general for regression coefficients that were derived on data with non-correlated input variables. For this, the formula is true. The derivation is not that straightforward. That's why we're not going to cover this here in this lecture. Let's conclude this chapter by looking at a numerical example with our 2-bar truss. And we're going to look at two design variables, E, the Young's modulus, and A, the cross-sectional area, and pose the question, what design variable is more important or sensitive? We compute the Pearson correlation coefficient for the entire design space and come up with a value almost 0 with respect to E and a value significantly different from 0 with respect to A. We come up with two different gradient values, the numbers of which are different, but note that the dimension, the physical dimensions, of course, is also different. That's why you cannot directly compare them. Also, the gradient is computed for one particular design and not for the entire design space. And then we come up with regression coefficients, the numbers of which are different, but also the physical dimensions of which are different. So it actually turns out that the question of what is more important is not so easy to answer. You can compare correlation coefficients with each other because they have the same physical dimensions. You cannot directly compare gradients with each other. Neither can you compare regression coefficients with each other unless you normalize them. Well, when you compute correlation coefficients, you implicitly normalize. You normalize by the standard deviation of your of the variables that you're considering. So remember, the correlation coefficient was covariance divided by 2 standard deviations. So you essentially normalize the covariance by this standard deviation and this standard deviation, and that makes it comparable to something that is normalized with respect to this standard deviation and this standard deviation. That's why you can compare them, but the relevance of your result will depend on the space that you chose on which you computed your sample. So in other words, if I increased my design space for Young's modulus significantly, I may all of a sudden realize a very different correlation coefficient that is larger than the correlation coefficient with respect to the cross-sectional area. So technically you can compare the correlation coefficients, but the value of your assessment will depend on the correctness of your normalization. You cannot directly compare gradients with each other, and you cannot compare regression coefficients with each other unless you normalize them. And by normalizing them, you put in a weighting factor. Very important is also to remember that gradients give you information about local sensitivity, whereas correlation coefficients and regression coefficients are global sensitivity measures. So let us summarize today's lecture. What we talked about today was how we can analyze functions that we would like to understand as a whole. We would like to understand how design variables affect the output of those functions, and what design variables are relevant and what design variables are not. This is particularly difficult when functions are high dimensional or have high dimensional input, when they are nonlinear, and when they are only available as black box, meaning that we do not have access to formula. When these troublemakers are present, we can use a very important technique, which is sampling. And with sampling data, we can either produce scatter plots or derive sensitivity measures. As a general recommendation for sampling, I recommend random sampling if you do not have particular information about the structure of your function. Random sampling is really the technique to choose when you have nasty functions and you do not want to adjust your sampling technique to the particular properties of the function. For the sensitivity measures we talked about, you need to keep in mind that there are global and local sensitivity measures. For all sensitivity measures, you carry out some kind of normalization, and that will affect the assessment of relevance. You cannot directly compare regression coefficients or gradients because they have physical dimensions. You can compare them if you normalize them, but then again, normalizing will mean that you put in some weighting factor that will affect your final evaluation or assessment of the relevance of a design variable. This would be it for today. I see you next week in lecture number 4.